So good morning one and all, and welcome back to the class on tribology. So what we were dealing in the last class, can anyone let me know quickly? What was the topic we were dealing related to the last class session? Anyone, just within a matter of seconds, kindly let me know. Be quick. Yeah, who is going to tell me what we were dealing in the last class? You should speak, right? Okay, let me call Mr. Dhanush. Dhanush. Okay, Ishant is telling introduction to hydrodynamic bearing. Good. And what else we dealt
Ma'am,
about?
ma'am,
Yeah.
we spoke about hydrodynamic bearings, ma'am.
Yeah. So what we dealt mainly related to it? So mainly we dealt about what you mean by a bearing, and we studied about the different forms of lubricants, right? Then we associated what does the word exactly hydrodynamic mean. Then we associated to hydrodynamic journal bearings and few concepts related to it. What are the concepts we have to keep in mind while designing a journal bearing? So all these protocols, yeah, thumb rules we went on related to hydrodynamic journal bearing. So now before starting with either Petroff's or Reynolds equation, you should be knowing some about the terminologies. Okay, so what we use, which are associated to the nomenclature of the journal bearing, right? So I have shown you in the beginning only how does a journal bearing look like, the sketch also. Yesterday I was really busy, I forgot to share the YouTube link. Today I will do that work. Okay, so I have shown the sketch exactly how does a journal bearing looks like, right? So if we go back also to the diagram, so you'll be having an casing, so which will be having the shaft here. So around that you will be having an bearing liner. So in between we will be having a clearance in which the oil from the inlet will pass through in forming the required lubricant film, right? So the shaft itself here will be termed to be as our journal, right? So regarding this we have discussed the components which are associated with the bearings also. Now let us go with the nomenclature before proceeding, right? So now you can see the diagram here. This is an example for dry and this is an example for lubricated journal bearing. Okay, so here you can't see any lubricant film over here, and hence the name dry bearing. Okay, so here dry journal bearing, you can take an example of journal bearing only where there is no lubricant. And in the next figure, you can see that this is the diagram which is associated with the lubricated version, because you're putting the oil through the inlet and it is forming the required film across the surface of the bearing and the journal, right? So initially what happens, you have to understand. Suppose if you start the journal in clockwise direction, you can see the direction in clockwise direction if you're turning the journal without adding any lubricant. So what happens is the journal will start rotating across the side as shown in the diagram over here. It will not be towards your left, it will be towards your right. Just a second. हेलो, क्लास में हो, बाद में बात करती हूँ. हाँ हाँ हाँ, I'm sorry. So when there is no lubricant, what happens is the journal will move towards your right as shown in the diagram. Once the lubricant is introduced, then the journal will pump out, right, with the lubricant film. So it will be well stabilized with a film of lubricant around, and as a result it will be forced to move towards your left, but still it moves in the clockwise direction. Since at that condition it forms a wedge shaped space, so the space which is here formed in between the journal and the bearing will be in the form of a wedge shaped. Okay, and hence it will move slightly towards your left. So this is how the movement of the bearing will be with and without the lubricant. So by observing only you can understand whether you have an oil film of lubricant or not. And seeing the direction and seeing the side in which the journal is there, whether towards your right or towards your left, also you can identify whether it is a dry version or a lubricated journal bearing. So this is the difference between how a journal runs with and without lubricated film. Right, so this is the thing mainly I wanted to make you understand, and rest the rotation will be in the clockwise direction in both the case for the journal, so no much difference associated with it. And then you should know what do you mean by H naught. You can see here a small gap, right, in between the journal and the bearing, right, a small gap in between, which is the minimum amount of clearance which is associated across the surface of the journal and the bearing. So this distance is nothing but called as the minimum film thickness. So the minimum film thickness will be represented by H naught, and it usually occurs at the bottom of the bearing across the clockwise rotation in which it is rotating. It will move towards our left, right? So this is the distance which you measured across the bottom of the bearing where the journal moved towards the left. So this direction, the distance which is left out will be nothing but our minimum film thickness. So from here onwards, if we tell H naught, you should understand it is the minimum film thickness what we measure towards the bottom of the bearing in which direction the journal has moved due to the addition of lubricant film. So this is about the terminology H naught, what you should be knowing. Apart from that, so here you can just see the entire sketch of the journal bearing, right? So you have to still more understand the nomenclature associated with journal bearing. So you should be knowing what you mean by radial clearance. Yesterday also I told you the clearance value, which is between, I'll just show you the diagram and explain. Okay. Right, so here this is the clearance radiance what we are telling you, or else yeah, let this be also visible. So the clearance the radial clearance will give you the difference between the radius of the bearing and the radius of the journal. So you have the radius, so this is the radius of the journal, and this is the radius of the, sorry, this is the bearing and this is the journal. So the radius, so this is the radius of the journal, right? And then you have the radius of the bearing also. So if you take this distance from this center towards here, so this entire distance will be the radius of our bearing, and this will be the radius of the journal. So the difference between the radius of the bearing and the journal will provide us the radial clearance. So this value will be termed as the radial clearance, which provides the difference between the journal and the bearing in circumferential manner, and hence we call that as a radial clearance. After knowing what you mean by the value of C, you should understand what you mean by eccentricity. So this eccentricity could be measured by taking the difference between the radial clearance and the minimum film thickness. So what we dealt right now, so minimum film thickness is nothing but H naught, which is measured across the bottom of the bearing between the journal and the bearing, right, towards the left direction. So that value is our H naught. So if you take the value, if you take the difference between the clearance and the minimum film thickness, that will yield as with the value of eccentricity. So this eccentricity here you can identify. So this is the distance, okay, the value of E. And in other way you can determine the eccentricity ratio also. So eccentricity ratio will be from hereafter, which is nothing but E upon C. So E is the eccentricity value. So this is the eccentricity value E divided by the radial clearance C will provide us the eccentricity ratio. So if anyone tells that you have to determine the eccentricity ratio, then you should be knowing the formula to use. For that, first you should determine the value of eccentricity. You should be knowing the value of radial clearance, then you can determine the eccentricity ratio. So if it is called as an full bearing, if the journal is enclosed by the bushes. Okay, if it is not enclosed, then it is not called as the full bearing. And lastly, what you have to know is the partial bearing. So what is partial bearing? The angle beta. So here you can see the angle beta, right? So from here till here. So what do you mean by it? If you take the diameter from here, so this is a diameter of the journal, and if you extend here, this will be the diameter of the bearing, right? So here, yeah, the distance from here till here, so if you just stretch out, it will yield you in providing the angle. So this angle describes the angular length of the partial bushing. So bushing is provided for the entire thing. So if you want to determine the partial bearing, means you will determine the angular length of the partial bushing. Any angular length you can take. Usually we take from here till here. So this angular length is called to be as our partial bushing. So main thing what you have to understand is what do you mean, the difference between the dry and the lubricated journal bearing, the terminology related to H naught, and you should be knowing the radial clearance, eccentricity ratio, right? If it is enclosed, if you have an bushing enclosed across the journal, then you call that as a full bearing, right? So for partial bearing, you determine the angle beta. Beta will represent the partial bearing angular length for partial type of bushing. So this is about the terminology aspect. So once the terminology is being done, so then we have to go up with the Petroff equation. So to start off with the Petroff equation, you should be knowing some concept of our viscosity, right? Because we are using lubricant film, and lubricant film will comes with different grades with respect to the value of viscosity. The viscosity value can be high, lower, yeah, medium, depending upon what is the application for which you are using and which type of journal bearing you are using, and what is the amount of load or the pressure which is coming across the contact area. So based on this aspect, we select the lubricant with respect to the required grade. So with respect to that grade, the viscosity value also will be defined, right? So before going to the derivation of the Petroff equation, let us just brush out related to the viscosity aspects. So everyone know all lubricant will be having certain viscosity. So hereafter, when we use a film of lubricant of a particular thickness, so you can see that you have a lubricant layer of a particular thickness, you'll be having a top plate and a bottom plate, right? So if a film of lubricant of thickness H, so this from here till here, it is the entire thickness of the film what we are using. So this entire layer here will be the film of the lubricant. So the film of the lubricant here is of thickness H. So if this film of the lubricant is placed between the two plates, so this is one top plate and this is the bottom plate. So if this film of lubricant is held between the two plates, right? So here you can assume that it is moving with an velocity u. So the top plate here is observed to be moving with an velocity u, and the bottom plate will be held stationary. So when the top plate is moving and the bottom plate is held stationary, how will be the condition of the flow in the lubricant film? So obviously the layer of the lubricant film which is nearer to the moving plate will move in the same direction in which the moving plate at the top is moving. Wherein the fluid film or the lubricant film which is held near the bottom plate will be stationary. It will not move. So one side it is moving, another side it is held stationary, and hence the shear comes into the picture. But what about the layer of the film which is held in between these two plates? So the layer of the film, suppose it might be here, yeah, here, yeah, here. The condition of the flow, it depends upon what is the distance it is away from the fixed plate, right? So the intermediate layers, so all these layers in between are called as an intermediate layers. So these intermediate layers will move with some velocity, and that will be proportional exactly to the distance from the stationary plate. So if you consider this layer, this one as an intermediate layer, so then this layer of the lubricant film will move with some velocity, and that velocity will be proportional to what is the distance this intermediate layer is from the fixed plate or the stationary plate. So with this concept, now you have to consider the Newton's viscous effect. So here the fluid will move with the same velocity because the lubricant film is very near to the moving plate. And here the lubricant film is very near to the stationary plate, and hence the fluid or the film here will be held stationary. But other intermediate layers will be moving with a slight amount of velocity, and that velocity will be exactly proportional to the distance from which it is being held from the stationary plate. So this is about the concept, what you have to understand, how the fluid will move when you have one moving plate and one stationary plate. So with respect to that, you should be able to get an equation for shear stress. So due to this fixed plate and moving plate, a shear stress will be induced while the fluid moves on, and hence you have to determine the value of the shear stress. And one more thing, what we have dealt about is irrespective about the force or pressure what you apply in a Newtonian fluid, the viscosity remains same. It doesn't change. So with respect to Newton viscous effect, now we should able to conclude an equation for shear stress which is there in the fluid. And this shear stress will be directly proportional to the velocity gradient. So velocity gradient defines with what velocity the intermediate fluids are moving on. So we write the shear stress will be equal to force upon the cross-sectional area. But as per the Newton's effect, this is proportional to the velocity gradient, and hence you should determine the velocity with which it is moving. And I told all the intermediate layers here will be moving with some velocity which is proportional to this distance y. So the velocity gradient here will be varying with respect to the distance y which is away from the fixed plate. And hence the velocity gradient here will be represented by du by dy. So mu will be nothing but the representation of the viscous or the viscosity of a particular fluid. And hence, instead of writing force upon area with respect to our Newton's effect, we will come out with an equation where the shear stress will be equal to the viscosity value into the velocity gradient with which it is moving. So this is about the equation what you have to be very clear enough with respect to the concept of viscosity and how does it flow when one plate is moving and one plate is fixed. Any doubts here, students? Is this clear? Hello? Clear enough?
Yes, ma'am.
Okay. Yes. So now the same thing we are still proceeding further. So we spoke about the Newtonian effect related to the shear stress with respect to the velocity gradient du by dy when one plate is moving and one plate is fixed. Only when the plate is moving at the top and the plate is fixed at the bottom, you will be having the velocity gradient, the variation in the velocity with respect to the distance from the stationary plate. Similarly, we have to understand what happens when the velocity gradient is constant. So when the velocity gradient is constant, there will be no change in the velocity. All the fluid intermediate layers will be moving with the same velocity. And at that case, instead of writing du by dy, we directly write the velocity to be represented by capital U, and instead of y, it will be the total thickness of the lubricant film. So now we before we just focused the velocity variation of the velocity with respect to the distance. So now we assume that it is a Newtonian fluid, it is having the same viscosity and there will be no change in the velocity, right? It will be a constant velocity with which it is moving. Then instead of taking the small u and y, we have to replace that with the velocity capital U with which the entire film is moving, and at that time we have to consider the thickness of the film total, which is h, instead of y, which was the distance before considered with respect to the stationary lubricant stationary plate. So now equation slightly changes. So without considering the variation of velocity with respect to y, we will assume a constant velocity gradient at a particular thickness of the lubricant film, which is H. Then the equation will be changed into the regular equation is shear stress is equal to F upon A. So instead of F upon A, we are replacing that by the viscosity into the velocity gradient, which is constant with respect to Newtonian fluid, and H will be nothing but the thickness of the film. So there will be slight variation. So this is always referred when you have the variation in the velocity of the intermediate fluid layers. If you have a constant velocity gradient, then as per the Newtonian fluid, you have to go with this equation for the shear stress. And viscosity is represented by mu. So in SI system, so this is the unit what you have to follow. Okay, Pascal, right? So wherein in case of US system, you have different unit, and for that we have the conversion factor also, but usually we go up with the SI system. So this is about how to get the equation for the shear stress with respect to Newtonian fluid. So this thing you have to understand. So once the concept of the terminology, the nomenclature of the bearings is clear, journal bearing, and you know now how to evaluate the shear stress when and how the viscosity of the fluid keeps varying, whether it is a Newtonian fluid or a non-Newtonian fluid. So for both the things, you have the equation for the shear stress, which is developed due to the pressure or the load which come across the contact area where you have a film of lubricant, and that film of lubricant will be having some viscosity also, right? So this was a basic prerequisite concept what one has to know before going for the derivation part. So now let us start up with Petroff equation. So what do you mean by Petroff equation? We are just deriving an equation which gives or yields us the value of coefficient of friction associated to a journal bearing. So you know what you mean by journal bearing. You know like what you mean by friction, what is the equation we use to determine the coefficient of friction. So now we are correlating the known concept of journal bearing with the coefficient of friction in the form of a particular equation which was derived by the person Petroff, and hence the name to be Petroff equation. So this basically provides you the value of the coefficient of friction associated in any journal bearing. So before starting, what you have to consider is an assumption to be followed. So here the assumption what we follow is the shaft is concentric. So the alignment of the shaft is exactly concentric. Even though sometimes if the shaft is not concentric also, right, we assume that the shaft is concentric. But sometimes the shaft is not concentric, but the coefficient of friction which is predicted by this equation also turns out to be quite good. This is the clarification given by Petroff equation, because this fellow assumed that the shaft is concentric and derived an equation to yield coefficient of friction. But he is also justifying that even though the shaft is not concentric, but still if you use this equation to derive equation to get the value of coefficient of friction, but also the value what it predicts with respect to non-concentric version also, it will be reasonably good. So that is a substantiation what he is giving for the assumption what he has taken while deriving this equation. So this thing you have to keep in mind. Right. So after this assumption, what you have to understand here is the shaft radius here is considered to be as r, which will be rotating inside the bearing. And the rotating speed here is given by letter N. And the clearance between the shaft and the sleeve, you know, it is represented by the letter S. Okay, so and the clearance, this clearance will be filled with the lubricant film or the oil. So when you fill the lubricant film across the surface and the bearing, usually sometimes there will be some leakages. But in this equation derivation, it is assumed that the leakage is very less or negligible. So these are the basic concept what you have to keep in mind while deriving the Petroff equation. Right? So now we have to start up related to the Newton's viscosity equation. So only I derived you the Newton's viscosity equation because you should know how that equation has come up. Then only we can go up with the Petroff equation. So here, since we are assuming a Newtonian fluid, so we are assuming that the velocity gradient is constant and we are using capital U as a constant velocity gradient. So here you can see the shaft and this is the length of the bearing and this is the radius of the shaft and this is the clearance. The value of C will provide you the clearance between the bearing and the shaft. So this distance is associated to be as small c, the radial clearance across the surface and across the journal and the bearing, and the small l will be the length of the bearing. So these are the terminologies what you have to understand, and this is the direction in which the load is acting across the center. So to start up, we will write down the Newton's viscosity equation. Right, so you know that shear stress here is equal to viscosity into the velocity gradient, constant velocity gradient upon h. So you also know what do you mean by h. What is h here? Can anyone tell me? We dealt in our nomenclature. What is h here? Yeah?
Oil film thickness.
Yeah, minimum oil film thickness. So then later we are now replacing with some values. So now this is a constant velocity gradient. So velocity you have to replace with some terminologies. So velocity, you have the journal and the bearing, right? So with what velocity is moving, it is associated with the circumference of the journal. So you'll write 2 pi r and the speed with which the bearing is rotating is nothing but represented by n, as I told you previously, the rotational speed of the bearing. So we are writing n and upon c. So instead of h, here we are taking the value of the clearance. So this will be now the change in the shear stress equation what we are formulating from the viscosity equation what we derived in the previous slide. So this is how now the shear stress will be changed. So then we have to see that the force needed to shear the film is given by the equation force is equal to shear stress into area, cross-sectional area. So shear stress is equal to force by A. So the same thing here now we are formulating because we need what is the force needed to shear a film of lubricant. For that F is equal to shear stress into A. So in that we know that the area will be equal to 2 pi r into length of the bearing, right? So the same thing will be now used to get the value of the torque. So torque will be nothing but equal to the force which was needed to shear the film into the value of r. So what is r here? R is the radius of the given shaft. So this is how you will write the equation. But force here is nothing but equal to shear stress into area. So instead of force, you will replace it by tau into A and you have R. So now the torque will be equal to shear stress into the area into the radius of the shaft. So once you have derived with this, then you have to substitute the value for A and get the required torque value, right? So then you substitute like the value for tau. So the value of tau here is how much? It is mu 2 pi r n upon c, and then A is nothing but 2 pi r l, right? And then we are left out with the value of r. So you substitute all the values, then the torque value will get yielded as 4 pi square r cube L mu n upon C. So this will be the equation for the torque which is subjected in the journal bearing. So this is how you have to correlate and get the value of torque. So this is the equation what you have to use to determine the value of torque in a journal bearing. And then we have to also come across the pressure which is exerted across the contacted area. For that now we are speaking with respect to the pressure. So what happens here basically, the pressure on the projected area will be given by W. So this is a pressure. Suppose at the center you have the pressure acting. So the pressure in the projected area will be equal to W, the weight here which is acting in downward direction, divided by 2 into R into L. So R will be the radius of the shaft and L will be the length of the bearing. So to calculate the pressure on the projected area, we have to use the equation W upon 2RL. So from this, we can calculate what is the net load acting across a projected area. Because in journal bearing, it will be able to withstand a huge amount of load, right? So to calculate, you will take W is equal to twice the radius of the shaft into the length of the bearing into the pressure. So this will be the equation for the calculation of the weight. So once you know the value of W, so now you will be calculating the torque created by this frictional force. So when you have some load acting, obviously the frictional force comes into picture. So when you have a frictional force into the picture, what is the change in the torque you are getting? So that you have to determine. Initially we use the equation torque is equal to force into R. But now it is associated with the frictional force which is generated or created due to subjection of the load across the projected area. And hence we now replace the value of F by the frictional force, and frictional force is associated with the letter a small f into W. So torque equation now gets changed into Fw times the radius of the shaft. The same equation, only thing the value of F changes here into frictional force. So then after writing, what you have to write is, so F you will retain as it is. You know the value of the load here, W, which is 2RL into P. So you will write down that, and R is remaining here, which is the radius of the shaft. So you will write down here. So finally, the value of T will be equal to 2R square FLP. So this is the equation what you have to use when there is a subjection of frictional force due to the load across the projected or the contacted area. So this is how you have to change the equation of torque based on which is the force which has been subjected to. So you have two values now. So by using these two values, when you equate these two values and solve, it helps in getting the value of coefficient of friction. What was our main goal? The main goal was to derive the coefficient of friction, right, for the journal bearing. So finally we are now, when you solve these two equations, in this equation you have the value of F. So you have to determine the coefficient of friction. right, due to the frictional force. So you'll derive the coefficient of friction, you will equate these two, and this will yield in the value 2 pi square mu n upon p into r by c. Don't write all the numerical aspect here together. You have two bifurcations. Mu n by p is different, r by c is different. I'll tell you what does it mean in the next slide. So if they ask you to derive the Petroff equation, then you have to start up with the basic assumption and the concepts what we have dealt, right? And then you should start up telling with the Newton's viscosity equation, and then you have to write the equation for force and torque without frictional force. Then you have to speak up with respect to the load, and as a result, due to the load, you'll be having some frictional force coming into picture. Then the torque equation again changes. Then you equate both the equations to get the value of coefficient of friction. So this will be nothing but our Petroff equation. So in this, I told you we have two parts, right? So basically, this is the coefficient of friction equation derived by Mr. Petroff, and hence it is also called as Petroff's equation for the journal bearing. So to calculate the coefficient of friction in any journal bearing, this is the formula what we have to use. In this, you have two separate quantities. One is mu n by p. I told you have to write it separately, and r by c. So these two quantities are non-dimensional. It is not n-dimensional quantities. Okay, and these are very important parameters one has to consider in association to lubrication aspects. Why? Because these are used to give the bearing characteristic number, या Sommerfeld number, right? So this is called as a Sommerfeld number. So here Sommerfeld number or bearing characteristic number will be represented by the letter S. So S will be equal to mu n upon P into R by C whole square. Okay, so this equation will always give you Sommerfeld number. So if you substitute the values, anyhow you'll be knowing the values of all these. So if you substitute and calculate, it will yield you what is the bearing characteristics number, because there will be an entire list of different bearing and its characteristics. So you can associate with the help of this bearing number, you can know what are the characteristics of that particular bearing. So this value will help you to know the characteristic behavior of a particular bearing. And hence it is very essential to know what is the importance of Sommerfeld number. So this number is very important in even the lubrication analysis, because it contains many of the parameters specified by the design engineer related to this design of the journal bearing with respect to the lubrication aspect. Okay, so as a tribologist, if you tell a bearing value number for Sommerfeld number, he'll be able to give you the entire characteristics of that particular bearing. Okay, so this is very much in importance to know or figure out the Sommerfeld number from that of coefficient of friction. Okay, so this is about the derivation of Petroff equation. Is this clear? Any doubts? Any doubts? Yeah, usually they ask you to derive, you should be clear enough. So further, you should be knowing the Reynolds equation and all. So before going, still some theoretical concept is essential. So now I'm just figuring out the word called to be as stable in association with lubrication. And hence, it is termed to be as a stable lubrication. When you can call the lubrication as to be stable or unstable, that you should be able to identify. So for that, I just wanted to explain some concepts, how you can clarify whether it is stable or unstable, right? So here it is neatly explained to you all. Kindly do observe the difference between the boundary film and hydrodynamic lubrication can be explained by the figure. right? So here you can see an graph which is plotted. You have the coefficient of friction value along the y-axis and you have the bearing characteristics. So bearing characteristics will be given by that Sommerfeld number, which is basically mu n upon p. Okay, so this value is plotted along our x-axis and coefficient of friction is plotted along our y-axis. So here is the value of C. You know the value of C, what is the clearance value. So before and after the clearance value, how the film of the lubricant will be unstable and stable. So that is what you have to understand. So here you have to see, suppose if you are operating to the right of the point C and something happens and it results in increasing the temperature of the lubricant. So this happens related to the lubricant film what you are using. Initially we described where that it go. I think it is there in the nomenclature yeah before this, right? So without oil film you'll be having the journal which will be moving towards your right, and when you add on the lubricant film it move towards your left, right? So this is the minimum film thickness, what we call it as to be the H naught, and the value of C is nothing but the clearance value between the radius of the bearing to that of journal. So you should be knowing. So due to the lubricant film, what happens is the journal will move towards your left. So this you have to understand. So without lubricant, it will be moving towards your right. So the same concept we are now using for our stable lubrication. Suppose if the journal is operating to the right of the point C, which is the clearance in between the radius of the journal and the radius of the bearing. And suddenly, if temperature of the lubricant increases, what happens in this condition? The temperature increases. So when the temperature increases, obviously the viscosity comes down. It cannot retain the same viscousness when the temperature is high. It starts melting and the viscosity of it will reduce, right? So it results in the low value. And due to viscosity reduction, the friction associated with it also will be reduced, right? And due to which the shearing in the lubricant also will be down and the temperature will be also down. And this is called to be a self-corrected stable lubrication. So this will happen only if the film of the lubricant what you are using is thick. So if you have a thick film of lubricant, even though the temperature rises and viscosity comes down, it can substantiate the friction which is coming across the contact area, right? And the amount of heat generated due to shearing. So shearing happens in the lubricant because you might be having one surface which is moving, that means to say sliding or rolling, and other surface might be stationary, all right. So due to that, some small amount of shearing comes into picture. So even though the shearing comes down and temperature comes down, it will be stable, it will correct by itself because you have a thick film in it, and hence it is called to be as a stable lubrication. Next, you have to understand about the unstable lubrication. So what happens in unstable lubrication? Suppose if we operate to the left of the point C. So once we started operating towards our right. So the first condition, you are operating towards your right where the lubrication film is thick. So due to thick film, irrespective of the condition changed suddenly, it was able to correct by itself because it was able to stabilize, and because you are using a thick film of lubricant. So it helps to stabilize by itself, self-correcting, yeah, self-healing, yeah, whatever. And hence it is termed to be a stable lubrication. Suppose if we operate towards the left of point C, means you are using a thin film lubrication here. So you are using a thin film lubrication, and if the temperature is increased, obviously the viscosity comes down, but the friction here increases because it is a very thin film, and the viscousness what was there in the film has still reduced because of high temperature, right? And due to the reduced thin film, the metal to metal contact will be more, as the viscosity is coming down and as the friction increases. And due to the friction increases, the heat generated also increases. And as a result, it results in the damage across the surface of the journal and the bearing. And hence, the lubricant what we are using will be termed to be as an unstable lubricant. So to make the smooth flow across the bearing and the journal, we should always see that the required film of the lubricant is met or achieved. So you have to always see that mu n upon p value will be greater, equal to 1.7 into 10 raised to minus 6. So this is the value one has to calculate and check whether it lies within 1.7 into 10 raised to 6. Then you can say, claim that the lubricant what you are using is an stable one, or else it will be termed to be as unstable. So this is what I just wanted to explain related to the stable lubrication. And after that, I have spoken related to the terminology already with you all. When it is a stable lubricant, you mean to say that the film what you are using is of thick film. So when you use a thick film, the amount of friction which comes into will be dropped down. And I also explained how the bearing moves without lubricant and with lubricant, and like what is the minimum film thickness, and also the nomenclature of the journal bearing is being done. So in the next class, we will start up with the hydrodynamic theory, and then we will derive the Reynolds equation, right? So I won't go into the depth explanation of hydrodynamic theory. I'll just tell you within a matter of minutes what is exactly we will be doing in the next class. Okay, so here hydrodynamic theory was developed by doing some experimentation. So it was conducted by Mr. Tower. So Tower conducted an experiment to understand what is hydrodynamic theory basically. So for all the experiment data which is done, it has to be substantiated or validated by some analytical method or by mathematical model. So the person Reynolds developed a mathematical model to justify the experimentation data done by Mr. Tower. And hence the mathematical model which is derived by Mr. Reynolds is termed to be as a Reynolds equation. So if they ask you to derive the Reynolds equation, basically you are explaining the mathematical model to show what exactly the hydrodynamic theory is, and it helps to map the experimental data which is conducted by Mr. Tower. So Reynolds equation basically deals with our hydrodynamic theory. So Reynolds made some assumptions before doing the mathematical model. I'll just explain you the assumptions and leave it. Okay, the entire derivation and the concept will be done in the next class. So he assumed that the film thickness is very small compared to the bearing radius. So this is the assumption what he took. And as a result of very negligible thickness, he neglected the curvature. Okay, so that I will tell you exactly what it is. And secondly, the lubricant what he used was a Newtonian lubricant. So that is the assumption he told, where the viscosity remains constant. When you have a constant viscosity, it cannot be compressed. So it was incompressible viscosity, which was a constant one. And one more assumption what he took is the forces which come across due to inertia in case of the lubricant were neglected, and the film pressure which come across in the axial and the vertical directions was assumed to be constant, and the leakages which are associated with respect to the lubricant was negligible was or assumed to be neglected only. So no side leakages related to the lubricant was being considered, and hence it was in a unidirectional. And lastly, the velocity of any particle in the given lubricant depends on only x and y coordinates. So this was the last assumption what the Reynolds followed. So these were the set of assumptions the Reynolds followed to justify the experimental work done by Mr. Tower to give his equation for the hydrodynamic theory concept. So what exactly is, how we have to analyze, so that we will do it in the next class. So hope the concepts are clear. If you understand the concept, you can derive the equation by your own. Any doubts, students? Hello?
No, ma'am.
Yeah, so kindly go through it. And few of the students have not submitted assignments. It shows that you don't need the marks for it. If anyone have not submitted the assignment, kindly do it up. As the date has been crossed, the marks gets reduced. So please, just an humble request, do complete your assignments on date. So everyone type your name and USN in the chat room. I haven't brought my register today. I'll just call the students, those who are available in the class, and rest will be marked absent. Akhil KV. So see that you write your name and USN Pakka in the chat room. Akhil KV. Anil Kumar.
Present, ma'am.
Ankesh Aman.
Yes, ma'am.
Balaji.
Ma'am, Gautam.
Yeah, Gautam, your name was not displayed here. Okay. No, I'm not calling as per the roll call. I'm just calling here with respect to the student list. I don't have
Okay.
my attendance register here.
Okay, ma'am. Yeah.
Balaji VR,
Yes, ma'am.
Belder Muhammad Akram,
Yes, ma'am.
Chaitanya,
Yes, ma'am.
Chetan Kumar,
Present, ma'am.
Dhanush,
Ma'am, there are two Dhanushs, ma'am. Which one, ma'am?
Dhanush Natampalli,
Ma'am, present, ma'am.
Dheeraj,
Present, ma'am.
Dhyanesh, okay, Eshant, Gautam Krishna,
Yes, ma'am.
Gunasagar,
Present, ma'am.
Harshit,
Present, ma'am.
Himanka, okay, Kanishka,
Yes, ma'am.
yeah, Gautam Sai,
Yes, ma'am.
Sri Nagamurli Krishna, okay, Kunal Raj,
Present, ma'am.
Meghnath,
Present, ma'am.
Mohammad Ayan.
Present, ma'am.
Please be regular, Mohammad Ayan. You're continuously regular. Mohammad Junaid. Okay. Shri Prasad.
Yes, ma'am.
Niharika.
Yes, ma'am.
Nikhil.
Yes, ma'am.
Nirav.
Yes, ma'am.
Prajwal.
Ma'am, it's Prajwal, ma'am.
Prajwal S. Bhatt.
Present, ma'am.
Ranveer Singh. Absent. Rasik Baran. Rasik Baran is also absent. I don't know where he is. Rishabh Pandey.
Present, ma'am.
Rohan.
Present, ma'am.
Roshan Yadav. Sagar Datta.
Yes, ma'am.
Everyone kindly type your name and USN in the chat room. Sagar GV.
Present, ma'am.
Sanjay Raghav.
Present, ma'am.
Shiv Krishna. Okay. Shiv Pavan.
Present, ma'am.
Srinivasalu.
Yes, ma'am.
Subramanya.
Present, ma'am.
Tirumani Sethi Rohan.
Yes, ma'am.
Ullas.
Present, ma'am.
Vidyan. Vidyan is absent. Varun.
Present, ma'am.
Pavan.
Present, ma'am.
Okay. Anyone name whom I haven't called? Fine, then I will share you the link for the quiz. Yesterday also I was totally busy. I could not do it. Okay, so I'll just add on both the quizzes together by today. So you kindly give the quizzes as per the questions. Okay, Vidyan is present. Okay. So kindly type your name and USN also, Vidyan. As I don't have the register, I have to refer the name and details in the chat room as on proof. So kindly type. Anyone who haven't written, kindly do type it out immediately. So please take care then. Have a nice day until we meet in our next class. Bye-bye.